Hello, everyone. Today we have Raphael Yuster from University of Haifa talking on Hamiltonian cycles above expectation in R graphs and quasi-random R graphs. It's a pleasure to have you as our speaker today. It has been many talks. So it is like our almost last talk of until the summer break. So we are very glad you could make it after all the teaching. So you can start. As always, the question and answers will be at the end, but if you meanwhile have any questions, feel free to write in the chat, or I don't know if you mind if people just unmute themselves and ask you a question.
No, that's fine.
Okay, cool.
Okay, thanks, Liana, and the organizers for inviting me. Indeed, I'll talk about counting Hamilton cycles in uniform hypergraphs. So a brief outline of the talk was, I'll start, of course, with the introduction and some definition of the problem. And then I'll overview three results. The common theme of all of them is that we are looking at the maximum possible number of Hamilton cycles in a graph or hypergraph with a fixed density. For example, density 1/2 in various settings. So the first result will be just the setting of graphs and also quasi-random graphs. The second setting would be quasi-random hypergraphs. Already for r equals 3, there turns out to be a big difference between the graph setting and the hypergraph setting. And the third result that I'll go over, or at least state, is about a hypergraph without restriction of being quasi-random. And in the second part of the talk, I'll actually look at the second result, the one about quasi-random hypergraphs, and I'll give an overview of it for the case of 3 uniform hypergraphs, which makes the presentation much simpler, not because 3 is smaller than R, but because really there are things in 3 uniform that are much easier than already 4 uniform hypergraphs. But the main essence of the arguments, they carry over to larger R. And I'll end, of course, with a few open problems. Okay, so throughout the talk, I denote as usual by K and R the complete R graph on n-vertices. R graph, I mean R uniform hypergraph. And we say that an R graph has density P if its number of edges is P times n choose R. And what we're interested in is a very basic problem, that the maximum number of Hamilton cycles in R graphs with a given constant density. Okay, some constant density, P between 0 and 1. And now, of course, counting Hamilton cycles in various settings is not a new problem. It has been looked at various angles by quite a few researchers. Here is a partial list of, I think all of these papers wrote at least 2 papers on this topic, so this was some criteria. And there is just listed alphabetically, and there is no paper by all of these authors together. So, things that were looked at were a number of Hamilton cycles according to minimum degree, or in random graphs, or in tournaments, and such other settings. So let me first start by what I mean by Hamilton cycle in a hypergraph. So this is what is usually called tight Hamilton cycle. So a Hamilton cycle for me in this talk would be just a permutation of the vertices, such that any R consecutive vertices in the permutation form an edge. Of course, we think of this cyclically modulo n. So we can see that we can actually identify a Hamilton cycle with its permutation, and there are 2 n permutations corresponding to each Hamilton cycle, because reversals and rotations do not change the set of edges. of that cycle. So in particular, KNR has precisely n-1 factorial over 2 Hamilton cycles, tight Hamilton cycles. Okay, so another notion I like to use, the notion of an R set. So given a permutation, the R set are just the set of n edges it would have had in the complete uniform hypergraph. And every R consecutive vertices on the permutation, they are an edge. They are an element of the R set. Okay, so we want to count. So of course, I'll denote by h of g the number of Hamilton cycles in a hypergraph G. And of course, also that for any density that you give me, any constant density, on the one hand, there will be R graphs with this density, which are non-Hamiltonian at all, perhaps even non-connected. And on the other hand, every R graph with density P, it cannot have too many Hamilton cycles because it's still far from being a complete hypergraph. So the parameter of interest here is the maximum, yes, HR, call it HR and P, the maximum value of maximum number of possible Hamilton cycles in a hypergraph, in R graph with density P. Of course, I always assume that n is such that P is rational and n is such that P n choose R is an integer, just so that it'll be something to talk about. Okay, so to try to evaluate this maximum, this HR and P, it's natural to first look at what happens in random settings, because this at least will tell us what HG typically is, and it will more or less serve as a lower bound for HR and P. And indeed, this approach of comparing to the random object is also taken in most other papers on these counting problems on Hamilton cycles. So the two natural models we usually start to look at are, of course, GR and P, every edge independently with probability P, the Erdős-Renyi model, and the GR and M, where we just choose precisely P and choose R edges, M equals P and choose R. This is the model GR and M. So what's immediate? It's immediate that the expected number of Hamilton cycles in GR and P is precisely P to the n times the number of Hamilton cycles in the complete graph, right? Because every permutation, the probability that it turns out to be a Hamilton cycle would be P to the n. So this quantity, yes, P to the n-1 factorial over 2, we like to give it a name because this is what we'd like to compare to. So we'll call it ENP throughout this talk. So ENP is P to the n-1 factorial over 2. Just one thing that's obvious, we cannot just say that this ENP is a lower bound for HR and P. It's the expected number in the random hypergraph, but if I draw a random hypergraph, the density was not necessarily P. The expected density is P. It could have lower density, and the number of edges is positively correlated with the number of Hamilton cycles. So I cannot just say that ENP is a lower bound for HR and P. On the other hand, for GR and M, yes, where the number of edges, where I'm guaranteed that the density is what I want, but in the model GR and M, it's easy. It's an easy exercise to see that the expectation is just barely, slightly less than ENP. Okay, less by a small constant factor. But of course, in the GRNM, it does serve as the expectation does serve as a lower bound for HR and P, because every element in this probability space is of density P. So we start by getting that HR and P is at least ENP times constant, small constant. So we have some lower bound to start with. But who says this lower bound is also close to the upper bound? Maybe you can construct a hypergraph with much more Hamilton cycles. Maybe HR and P is significantly larger than the expectation value. than this E and P? And if so, how much larger? How much larger can it be? So this is the question we want to ask. We want to compare the ratio between HR and P and E and P. And the answer is yes. Yes, HR and P can be larger than E and P, but how much larger, that depends a lot whether we're talking about graphs or hypergraphs. And it depends a lot, and it depends such in a very, even in a very strong sense, then I want now to make it precise. So let me give one definition of quasi-randomness in hypergraphs. There are several non-equivalent ones. Here is one definition of quasi-randomness. So what is an epsilon p quasi-random R graph? Well, if it's a graph with n vertices, density precisely p, and every subset of vertices, well, enough to look at subsets of 50% of the vertices. Every subset of vertices of 50% of the vertices, the sub-hypergraph it induces also has density p plus minus epsilon. For graphs, this definition is equivalent to all other definitions of quasi-randomness, as was shown by Chang, Graham, and Wilson in their seminal paper. But that's not so for hypergraphs. Already for 3 uniform hypergraphs, this definition that I just stated is what is called weak quasi-randomness. There are other notions, stronger notions of quasi-randomness, first defined by Frankel and Rodel and very nicely surveyed by a paper of Gowers, who showed these distinct models of quasi-randomness. But let me just say that all of the results that I'm going to mention from now on, whenever I say quasi-random, they will apply to all models of quasi-random hypergraphs. This is the one I stated here is just the simplest one to state. But everything I'll say will hold to all models of quasi-randomness in hypergraphs. Another thing to observe that if I take an element of GR and M, then almost surely it will be epsilon p quasi-random. That's very easy to check. Yes, every subset of vertices has the right density up to plus minus a little bit. So we already know that the expected number of Hamilton cycles in GR and M is just a bit lower than E and P. On the other hand, it's almost surely a quasi-random hypergraph. So let's try to look what happens indeed in quasi-random hypergraphs. How many Hamilton cycles can we get there? So let me add just one more parameter, HR NP epsilon, the maximum number of Hamilton cycles over all epsilon p quasi-random R graphs. So if I just don't care about quasi-randomness, it's just like saying epsilon equals 1. So this is our HRNP. Okay, so HRNP epsilon is restricted to epsilon p quasi-random hypergraphs. So the meta question here is just to determine asymptotically how much larger can the maximum be compared to E and P, compared to the random setting. And we know that it's lower bounded by a constant factor because of GR and M. Yes, we've already seen that. But how much larger can it be? What's this ratio? So from the theorems that I'll state later, the following will follow. Let's start with graphs. So for graphs, this problem 1 is actually upper bounded by a polynomial in N. Yes, you cannot have the number of Hamilton cycles much larger than the ENP. The factor would be only at most polynomial in N. Already for 3 uniform hypergraphs, it will actually be lower bounded by an exponential.
Sorry, can I have a question? So in that polynomial, so what is the role of epsilon in that polynomial?
The role
if
of
any?
None. The role of epsilon is none. It will hold for all epsilon. It will appear in the constant terms. Okay, not in the
so you can say something even for epsilon equals 0.1.
I can say something even for epsilon, which depends on n, 1 over n to the 0.1, even for that. Okay. Okay, so for hypergraphs, it will be lower bounded by an exponential in n. Let me, perhaps before I talk about hypergraphs, let me say another thing about graphs. I don't even know how to, so we can upper bound it by a polynomial in n for graphs, but I don't even know how to lower bound it by a polynomial in n for every epsilon greater than 0. Okay, so I don't know how to lower bound it by a polynomial in n. I do know how to lower bound it by a polynomial in n if I don't care about quasi-randomness. So let me raise the following specific problem about graphs. Okay, is there some gamma greater than 0, say 1 over 100, such that for any density, fixed density, and for every epsilon greater than 0, quasi-random graphs, the number of Hamilton cycles divided by the expected number, is at least n to this 1 over 100 or 1 or n to the some gamma. Is there some gamma? I don't know. So this is an open problem. Okay, so let me now go over the results. As I said, I have 3 results. I'm going to mention 3 results on various settings: graphs, quasi-random hypergraphs, and hypergraphs. So let's start with graphs. So this is the first theorem. It's actually the easiest of all theorems, and I'm not going to prove it. I'm just going to state it. So for graphs, just graphs, no quasi-random, no quasi-randomness here. Okay, graphs with density p. The maximum number of Hamilton cycles divided by EMP. It's lower bounded by square root n, and upper bounded by another polynomial in n, n to the 1/2 plus 1 over 2p. Okay, so it's polynomial in n, both in the lower bound and upper bound. Let me say that the upper bound is really just an adaptation of a result of Alon, of a method of Alon, by looking at the permanent method he used for Hamilton cycles in tournaments. The lower bound here is a bit more tricky, because for every possible density p, and there are some problematic densities, we have to construct Hamilton cycles with precisely this density, and which have many Hamilton cycles. So for some densities, we can do it rather easily. For some densities, I don't have an explicit construction, and the construction is also probabilistic, is only probabilistic. So this is the result about graphs. Actually, I was surprised to see that it wasn't known. Okay, but there we go, we have it. Now I want to switch over to hypergraphs. So in hypergraphs, it turns out to be more involved. The proofs turn out to be more involved. So the second result is probably the main result, is about quasi-random hypergraphs, starting with 3 uniform. So HR NP epsilon, maximum number of Hamilton cycles in epsilon p quasi-random hypergraphs versus NP. Here the ratio would be at least 2 to the n to the gamma, and we can get gamma close to 1/2, starting from uniformity 4. Actually, we stay at 1/2, even if the uniformity increases to 5, 6, 7. I don't know how to get larger than 1/2, but at least it's exponential. For 3 uniform, I just get 1/3. It doesn't matter. The point is that it's exponential. The ratio is exponential. But notice that the big difference between theorem 1 and 2, not only with respect to the exponential thing. So in theorem 2, we already get the exponential even if we limit ourselves to the quasi-random setting. Okay, and in theorem 2, we only have polynomial, even if we don't assume quasi-randomness. So it's very, very different. Finally, if we want to look at hypergraphs without restriction of quasi-randomness, So here is another result, just hypergraphs with density P, no quasi-randomness here, compared to E and P. So here the exponent can actually be made linear in M. This base is a number, of course, larger than 1. There is also an upper bound. An easy upper bound would be something like 1 over P to the power of N. So at least we know that the behavior for hypergraphs is some base to the power of N. I don't know the exact base, but this is the behavior, something to the power of N. Also about this result, which is more involved than theorem 1, but slightly less involved than theorem 2, I will not talk in the remainder of the talk here. What I do want to do in the remainder of the talk is look at theorem 2, the one about quasi-random hypergraphs. But also that I want to look at a special case, the case of 3 uniform, not because 3 is a nice number, but there's really a difference in the proof. There's something that we have in 3 uniform hypergraphs that we lose, some nice objects that we have in 3 uniform hypergraphs that we don't have in 4 uniform hypergraphs and above, and which makes the proof much more convenient to describe, but still keeping most of the ideas also apply to higher uniformity. The proof I'll show for 3 uniform will give me an exponent of the form 2 to the n to the 1/4 instead of 2 to the n of 2 1/3, but who cares? At least it will still show that it is exponential. Okay, so this is what I want to do in the next 20 minutes, is overview the proof for 3 uniform hypergraphs. Okay. So I'll make one additional simplification, but just this is really just for the sake of the ease of explanation, not because it really matters a lot. I'll assume that my density is such that 1 over P is an integer. And also I'll not prove it for all n, but only for when the number of vertices is satisfies some divisibility constraints. This is just for convenience. It will not be difficult to once I prove it for such P and such n, this will not be difficult to prove it for all densities P and all n. All n, of course, such that P times n choose R is an integer, of course. So here is a version. Here is the theorem 2 on this particular version. Suppose you give me epsilon and you give me a density which is such that 1 over P is an integer. And suppose also that n is of the form q to the 4 plus 1, where q is a prime power. And also that this thing here, pq cubed times this polynomial, suppose it's an integer. By the way, that's not something very demanding. For example, if p is 1/2, then 1 over p is an integer, and indeed, and q is a power of 2, that's fine. Then this would be an integer, so it's not very restricted. Yes, it does hold, say, for p equals 1/2 and q a power of 2. Okay, so if all this holds, then I'll be able to construct to you a 3 uniform hypergraph, which is epsilon p quasi-random, and its number of Hamilton cycles is large, much larger than E and P. How much larger? Exponential factor, 1 over P to the power of n to the 1/4. So before I start the proof, I want to recall a definition, Steiner system. So Steiner system SRKN, 3 integers r less than or equal to k, less than or equal to n. Well, what is it? I'm sure you all remember, but let me just, for the sake of completeness, say it. So it's a set L of k element subsets of 1 to n. We call these subsets blocks, such that every r element subset of n is contained in exactly 1 block. Okay, so that's a Steiner system. And if you like hypergraph terminology, then it's the same as saying that K and R has a pairwise edge disjoint decomposition to subgraphs isomorphic to KKR. That's the same thing. But the problem is that when R is at least 4, we don't have any Steiner system, not known and probably do not exist at all, any Steiner systems, when K, the size of the blocks, is polynomial in N. Okay, we need this for the proof. We need the size of the blocks to be polynomial in N. Of course, if K would have been constant, then surely there are because of the existence of designs. Yes, but it's not enough for us. We need K to be polynomial in N. Luckily, and this is why I said that the 3 uniform case would be much easier. Luckily for R equals 3, there is such a Steiner system. It can be constructed from finite geometries. In particular, when Q is a prime power and S is a positive integer, there is a Steiner system of triples, blocks of size Q plus 1, and the ground set of size Q to the S plus 1. Okay, so the blocks are of polynomial in the size of the ground set. That's important. This was a construction first observed by Hughes. For me, it will be enough to look at the case S equals 4. S equals 3 will not work. S equals 4 would be the best take. So I'll use the existence of Steiner systems with triples, blocks of size Q plus 1, and ground set of size Q to the 4 plus 1. So how many blocks does such a system have? It's very easy to compute. The number of blocks would be this thing, which is roughly Q to the 9. That's the number of blocks. And remember that in the statement of the theorem in the previous slide, I wanted certain conditions. Assume that N is of the form Q to the 4 plus 1. So that's fine, right? That's the ground set of the Steiner system. Q is a prime power, and that's okay. And I also wanted that the density P would be such that 1 over P is an integer, and this thing is an integer. But what is this thing? This is precisely P times the number of blocks. Okay, so I'm assuming that P times the number of blocks is an integer. By the way, the number of blocks in terms of N is N to the 9 over 4, right? Because Q to the 9 is like N to the 9 over 4. So if P times the number of blocks is an integer, and 1 over P is also an integer, then of course you can just partition your blocks into parts, call them L1 till LT, T being PL, such that each part contains precisely 1 over P blocks, a constant number of blocks. Well, everyone can do that, right? The numbers agree, but I don't want to just take arbitrary partition of the blocks. I want each part, each Li, I want all the 1 over P blocks in Li to be vertex disjoint. I'll need this. So is this possible? And the answer is yes, it's possible. It's a simple application of the Heinel-Semeredi theorem. Let's see. Let's construct a graph with whose vertex set are the blocks, and 2 blocks are connected if they have a non-empty intersection. So what do we want from this graph? We want a factor of independent sets of order 1 over P. Can we do it? So the number of vertices is roughly N to the 9 over 4. The maximum degree of this graph, that's very easy to compute. It's less than N squared, so the maximum degree is much smaller than the number of vertices. So by Heinel-Semeredi, we have indeed have a factor of independent sets of size 1 over P each. Okay, so I fix this partition of the blocks to parts. Each parts have 1 over P blocks in it, and the blocks are vertex disjoint. And now I'm going to construct the hypergraph, for which I want to prove that it has, with high probability, it has many Hamilton cycles. So here's how we construct it. The vertex set is n, q to the 4 plus 1, the points of the Steiner system. From each part Li, remember it contains 1 over p blocks, I'll choose independently, I'll do it independently for each part. I'll choose 1 out of the 1 over p blocks that it has and take all triples in it. Namely, I'll make it a k, q plus 1, 3. The other blocks in the part, the other 1 over p minus 1 blocks in that part, they will be edgeless. I wouldn't take any triple. So what's the density of the graph, the hypergraph I obtain? Density would be precisely p, right? Because I just took 1 block out of 1 over p blocks from each part. But another thing is obvious, that it is also with high probability, it's epsilon p quasi-random for every notion of quasi-randomness that you'd like in hypergraphs. That's because just the probability that an edge, that a triple would become an edge is just p, and there are not too many dependencies. Sorry about that. Each edge depends on how many other edges. Each triple depends only on triples belonging to blocks in its part. But the number of triples of blocks in its part is roughly q cubed, which is much smaller than n cubed, which is the total number of triples. So the dependency is very weak, and we can use, say, Johnson's inequality to prove, or even Chebyshev to prove that, no, we use Johnson's inequality to prove that it's epsilon p quasi-random with very high probability. Okay, so it's a nice object. It has the right density. It's almost surely quasi-random. But now we have to prove that it has many Hamilton cycles. So we'll prove that with high probability, it also has many Hamilton cycles, enough to guarantee the statement of the theorem. So let me look at some permutation of 1 to n. And remember the 3 set. Yes, the 3 set are all the possible edges it would have had in the complete hypergraph. So for example, if this is the permutation, then the 3 set would be 3, 1, 2, 1, 2, 4, 2, 4, 5, etc. So n elements in the 3 set. And now I want to define the notion of goodness for a permutation. It has nothing to do with the coin tosses that generated the graph. It just has to do with the way I partition the blocks into parts. Okay, I said that the permutation is good if no part Li, remember each part contains 1 over p blocks, if no part Li contains 2 elements of the 3 set in distinct blocks. It's allowed to contain more than 1 edge of the 3 set. Actually, it will be important for me that some of them contain more than 1 edge of the 3 set, but only as long as they are in the same block of that part, not in distinct blocks. So here's an example. Suppose this is Li, it has 1 over p blocks. Suppose ABC is in the 3 set, and also say DEF is in the 3 set. So that's fine. Yes, it has 2 elements. SPI has 2 elements, but in the same block. But if, for example, GHI would also have been in the 3 set, then that would be bad, because the 3 set contains edges from 2 distinct blocks of that part. We want no part to contain edges in 2 distinct blocks from the 3 set. Okay, so this is being good means that we don't have this situation. By the way, notice that if you have a bad permutation, then no matter how your coin tosses were generated, surely that the 3 set, this SPI, would not become a Hamilton cycle. For example, here, I just choose 1 of these blocks. Suppose I choose that block and made it into a clique. All the others were empty, so I didn't cover this edge. And if I chose that block, then I didn't cover these 2 edges. So if you are a bad permutation, then surely you don't give me any Hamilton cycle. If you are a good permutation, then we can compute the probability that you can give me a Hamilton cycle. So let's count in how many parts how many parts contain edges of the 3 set. Call this f pi. So the number of parts which contain edges of the 3 set, I'm doing it only for good permutations. Of course, it's at most n. The best case would be that every edge of the 3 set would be in a distinct part. So trivially, it will only one block of that part would contain its edge. But of course, it could be smaller. It's important for us to prove that on average it would be significantly smaller. That would be important. But given this notion of f pi, we can say precisely what is the probability that the 3 set would become a Hamilton cycle. From each part which contains edges of the 3 set, we want to choose the right block. There's one, so the probability that we chose that block is p, because it was one block out of 1 over p blocks. And we want this to succeed for every part which contains edges of the 3 set. So the probability is precisely p to the f pi. Okay, so the proof is just what I said now. Is what we try to do is prove that with high probability, most permutations are good. Bad ones are bad for us. They don't contribute to Hamilton cycles. And we also like to prove that for most good permutation, this f pi here is actually not n, it's significantly smaller than n. That would be the technical part of the proof. Once we do that, we can combine these two observations together with the fact that the probability is p to the f pi and get that the number of Hamilton cycles is large. So let's start with something easy, then that the number of bad permutations is negligible. Most n factorial n to the -1/4. Okay, so that's the same thing as saying that if you give me a random permutation, the probability that it will be bad is at most n to the -1/4. So let's take two triples of the 3 set of the permutation, say E and F. First of all, if these triples intersect, suppose 3, 4, 5, 4, 5, 7. So if they intersect, then surely they cannot appear in distinct blocks in the same part, because the blocks in a part are vertex disjoint. So we only care about two triples in the 3 set that are disjoint. Say 4, 2, 1, and I don't know, 7, 9, 6. So what's the probability that both of them will be in distinct blocks of a part in Li? So each edge belongs to some block in some Li. It's a Steiner system. So suppose you tell me to which block and to which Li E belongs. What's the probability that F belongs to one of the other blocks in that part? So fix a block. F is a completely random 3 set out of n minus the vertices of E, out of this n minus 3 vertices, because the permutation was random. So the probability that F would be a subset of that block P is precisely this amount, which is roughly n to the -9/4. But remember, there's more than one block. There are 1 minus P minus 1 blocks, but that's a constant. So even if you take the union bound, it's still n to the -9/4. And you want this to hold for all pairs of triples in the 3 set. The 3 set contains n elements. The number of pairs is n square. So even if you apply the union bound to this n to the -9/4 multiplied by n squared, it's still only at most n to the -1/4, which is what we wanted. So the number of bad permutations, those that surely do not give me a Hamilton cycle, is relatively small, actually very small. So the number of good permutations is large. It's almost n factorial. N factorial -1 minus theta n to the -1/4. So let's compute the expected number of Hamilton cycles in the object that I construct. Well, take it as a sum of indicator random variables. For every good permutation, we know that the probability that it becomes a Hamilton cycle is p to the f pi. So this is the sum. We don't forget to divide by 2n because of rotations and reversals. So this is precisely the permutation, the sum of over all good permutations of p to the f pi. It's not so easy to handle this. We want to lower bound this term, right? It's not so easy because f pi could be very different for different pi's, but there is a nice trick, a simple trick, but a very important one, which makes our life easier. Let's call f bar be the average of f pi over all good permutations. Then I claim that I can have that this value here, the expected number of Hamilton cycles, is at least the number of good permutations divided, of course, by 2n times p to the f bar, this average number. So why does this imply this? That's precisely the arithmetic mean geometric mean inequality, right? This is an arithmetic mean and this is a geometric mean. So it suffices to prove a lower bound for this guy because we want to lower bound the expected number of Hamilton cycles. So we have to manage this f bar, the average of f pi. That would also not be so easy. So I have to look at one almost final definition, something that I'll call g pi. And now I want to look at four tuples. So, or pairs of consecutive three tuples. So the four set of that permutation. Okay, four consecutive elements of the permutation. So you give me a permutation. I want to compute how many elements of the four set have the property that all of those four vertices in the four set are in the same block of the Steiner system. Okay, suppose 1, 2, 3, 4 is in the four set, then it contributes to g pi if 1, 2, 3, and 4 luckily occur in the same block. Why is that of convenient? Because g pi helps us to upper bound f pi. F pi is at most n minus g pi, right? Because whenever you have two consecutive triples that fall into the same block, then you save a part, right? You already use two elements of the three set inside the same part. So every two such triples, namely a four tuple, consecutive four tuple in the same block, saves me something for f pi. So we have that f pi is at most n minus g pi. By the way, it could be much smaller. I have an example here, but I think I'll skip it. So instead of upper bounding f pi, let's try to lower bound g pi. That would be easier. And again, because we wanted to look at the average of the f's, we need to look at the average of the g's, the average of g pi taken over all good permutations. Once again, that won't be so easy to compute, but here is finally something that's trivial to compute. Trivial to compute. G star bar. That's the last one, I promise. So what is G star bar? That's just the average of G pi over all permutations. We'll show exactly what it is. Okay, so we want to look at the average of the number of four tuples, consecutive four tuples of the permutation that occur in the same block. That all these four occurred in the same block. Looked at the average of them. Now we know that f pi is at most n minus g pi, which means that f bar is at most n minus g bar. I'll compute g star bar precisely. I'll prove, and this is the technical part, I'll prove that the average over all permutations of g is very close to the average of g over good permutations. And now, because we know that f bar is at most n minus g bar, and we will be able to replace it with something that we know to compute, g star bar, we'll have indeed an upper bound for f bar, which will imply a lower bound for this geometric mean, remember, which lower bounds the expectation. So here's something very easy. G star bar exactly equals nq minus 2 divided by n minus 3, which is theta n to the 1/4. In case you lost me, here's what I want to show. I'll take a permutation at random, and now take a 4-tuple, namely ABC is in the 3 set and BCD is in the 3 set. What's the probability that all of the 4 ABCD are in the same block? Well, it's very easy to show that it's precisely q minus 2 divided by n minus 3. But how many such pairs of triples in the 3 set do we have? It's exactly the number of elements in the 4 set, which is n. So we have to multiply this by n. So the expectation is precisely n, this quantity, which is n to the 1/4, roughly. So we know this G star bar precisely. The technical lemma, which I will skip because of time limitations. I have 5 more minutes or something like that, right? Is that true? Yeah, I think I can make it in 5 minutes. Okay, we'll prove that. Yeah, okay, so I will prove that the G bar does not deviate a lot from G star bar, the average all permutations. Difference is very small. That's the most technical part, which I'll try to skip. This is even even the outline I'll need to skip. But what is important for me is inside the proof, I defined the notion of a very bad permutation. A very bad permutation is one for which G pi is larger than, say, 6n to the 1/3. So just remember this. A very bad permutation is a permutation for which G pi is larger than 6n to the 1/3. And we prove here, we've proved, suppose you believe me, that I've proved that the number of very bad permutations is not large. It's at most n minus 2 factorial. So here goes. Let's first sum G over all bad permutations. So first of all, we know that there are not too many bad permutations. Remember, we already shown that. Something like n factorial, n to the -1/4. Out of them, at most n minus 2 factorial are very bad. Namely, their G is large. So for them, I'll use the trivial bound G pi less than or equal to n. For the other bad that are not very bad, we have the G pi is at most 6n to the 1/3. So overall, the sum of the G's over all bad permutations will be this amount, from which you can easily see that the sum of over bad permutation divided by n factorial is less than n to the 1/12. And finally, we can indeed compare the average over good permutations to the average over all permutations by this. Well, in the numerator, we have the sum of the G's of over good permutations, because this is the sum of all G's, minus the sum of the bad G's. So these are the good G's divided by the cardinality of the good permutations, which is greater or equal than to P is less than F factorial, right? So this is greater or equal than G star bar minus, I didn't touch this part. Now, P is very close to n factorial, so you can replace P with n factorial and write here 2 instead of multiply this by 2. And we've just shown in the last slide that this is roughly n to the 1/12. So we were able to show that the difference is negligible. So finally, expected number of Hamilton cycles. From the geometric mean, we know that it's at least this amount. Good permutation divided by 2n, p to the average of f. We know that the average of f is at most n minus the average of p. So we plug it in here. we know how to state G bar in terms of G star bar. This was the technical lemma we just skipped. So instead of G bar, we just plug this G star bar plus n to the 1 over 12. And we've computed precisely G star bar. It was roughly n to the 1/4, which eats this to n to the 1 over 12. So the expectation is this value, is at least this value. Okay, now we just plug in some values. We know that the number of good permutations is almost n factorial. It's certainly more than 50%. Remember that E and P was P to the n minus 1 factorial over 2, so plug this in here. And we know that the HRNP epsilon, the maximum number of Hamilton cycles, it is at least that expectation. Actually, I'm a bit cheating here because, you know, there is a very small chance that the graph that you drew will not be quasi-random. But of course, you can use Chebyshev to show that this expectation is this random variable is very, very close to the expectation. So it's okay to say this. Now just plug everything here in this inequality. So replace P with n factorial over 2, plug E and P, the value of E and P here, and you'll get that this ratio is indeed a constant to the power of n to the 1/4, like we promised to prove. Okay, so let me perhaps end with this, put up the slide, or at least put up the slide of maybe just very briefly state them. So first problem is to determine the maximum number of Hamilton cycles in quasi-random R graphs. Well, we know that this is the proof that I just talked about. We know that this ratio is exponential in n, where the exponent is of the form n to the x being very close to 1/2. I'm almost certain that you cannot get much larger than that. You cannot make x go towards 1, even if you increase the uniformity. What can you say about graphs? This is something that I posed before. The ratio for graphs, quasi-random graphs divided by E and P, can it be omega n to the, say, 1 over 100? We know that this ratio, without quasi-randomness, just the maximum number of Hamilton cycles divided by E and P, we know that it's some base to the power of n. What exactly is that base? Okay, so that may be interesting. And finally, perhaps interesting to look at other structures, not necessarily Hamilton cycles, other spanning structures in random graphs, and count them. So I think I'll stop here. Thanks. Okay, Liana, back to you.
Thanks a lot, Raphael. I invite everyone to unmute themselves for a round of applause for a great talk. Any questions?
So one question, that's basically your last problem. Is there any other structure that has been looked at other than Hamilton cycles?
Well, in the setting of graphs, graphs with bounded degree have been, spanning objects with bounded degree have been looked at. Yes, but for hypergraphs, I don't know of any such things. What? Okay.
Okay, yes, thanks. And so you mentioned this difference between the binomial random model and the uniform one. So the constant, is it difficult to get this constant correctly?
Precisely.
The difference between, yeah.
No, it's not difficult. It's not difficult. It's a simple exercise in probability. No, it's not difficult. It should be an easy exercise. It's like a hypergeometric distribution. I think should be easy.
Okay, thanks.
Any further questions? Okay, if not, then let's give another round of applause to Rafi.
Thanks, everyone.
So maybe, Rafi, maybe is one more question. Could you somehow, would there be a stronger notion of quasi-randomness where, you know, you would somehow kill all these design constructions? So, or
Yeah,
right, so
yeah, but my designs are a small polynomial in n, right? They are a size of n to the 1/4, for example. The objects, the blocks. So to kill that, you'd need your epsilon to be very dependent on n, say 1/√n or something like that. So, right?
yeah, okay.
The designs are polynomial in n, a small polynomial, so I don't see how to kill them. At least not all the usual notions of quasi-randomness won't kill them.
Mm-hmm. Mm-hmm.